All right. What I would like for you to do is I'd like for you to start off with our warm-up today. And I would like for you to find a space in our lab notebook. It does not have to be in the bell ringer section, but in your digital lab notebook, I'd just like you to answer these 3 questions. What causes Earth to experience seasons? Why are winters colder and summers warmer? And why is it always warm near the equator? So in your digital lab notebook, find a spot to answer these questions. It could just be fall under this unit materials for space systems. And you could write each one of these questions out and just answer them briefly in the best of your ability. Right here on the board. What causes Earth to experience seasons? Why are winters colder and summers warmer? And why is it always warm around the equator?
Hi, Kayla.
Do we have Kayla here now?
Yeah.
Okay.
Everybody's here.
My computer's slow.
I'm really slow.
If you have not done so already with your digital lab notebook, once it is completely loaded, if you click on the File button and then go and scroll down underneath where it says Download, there's a section that says Make Available Offline. If you click on that Make Available Offline, it should make your digital lab notebook a little more useful versus having to load it all the time.
Pardon the interruption, but at this time, we are going to start pictures. So freshmen, last name A through G, head to the gym. Sixth graders, A through G, head to the gym. Thank you.
Can I say answer questions too?
Answer all 3 of them, please.
I'm writing mine.
That's fine.
Maybe you should take your coming soon thing down. But it's coming soon. Picture day.
Yeah, I should have changed it to today, shouldn't I?
Yeah.
Today's
Yeah.
Friday.
That'll go away after today, and I'll put a new poster up on our virtual classroom. for other things that are happening. Like maybe what I can do is I can put a poster up for each one of the days for homecoming and what's supposed to be each day.
Oh, camo is Monday.
Yep. Those of you that are online, how many of you are still working on these 3 questions? What causes Earth to experience seasons? Why are winters colder and summers warmer? And why is it always warm at the equator?
I'm almost done.
I'm still working.
Almost done. Okay. Okay.
Still working.
Okay. Excellent. You guys continue to work then. Do we think maybe 2 more minutes, or do we need a little longer than that?
2 is good.
2 minutes.
Okay. I'm hearing online people think only 2 minutes. I've got a couple people in class that are thinking maybe more like 3. So we'll see where we are after 2 minutes.
All right, I'm done.
Okay. Excellent.
Oh, wait. I'm gonna do this right.
Okay. Once you're done, if you could go to our Google Classroom. And I posted under our Google Classroom, under the classwork, our What Causes the Season Lab. It's the last thing posted under Space Systems. If you could open that up. All right, we are going to get started with today's lab and making some observations. And right now it wants us to tilt our globe for question number 1A. It wants us to tilt it with the northern hemisphere of our globe tilted away from our light source. So we've got a light source, we've got our globe, we've got a northern hemisphere here, we've got a southern hemisphere here. As a little bit of review, we have come to the conclusion that the Earth is most likely spherical. We know that the sun rises in the east and sets on the west. Because of that, we are saying that the Earth must spin counterclockwise, because that would cause the sun's light to be coming from one angle, and if the Earth is spinning counterclockwise, if we're looking down from the North Pole, it would cause the eastern seaboard to see sunrise first. It would cause the sun to rise in the east side of our country, which is what we see, and it would cause the sun to set in the west.
Light's gonna be the sun.
At this time, we need H through M. The freshman class go to M, and for the sixth graders, H through M. Thank you.
No.
So again, the Earth must spin counterclockwise if we're looking down from celestial north. The reason that we're saying that is because the sun rises in the east and sets in the west. We have talked about the fact that it must be the Earth sits at a slight tilt, and the justification we had for that slight tilt was the fact that during the winter months we have the sun it doesn't get as high in the sky during the winter months versus the summer months. The sun seems to be much higher in the daytime sky during the summer months. What other observations did we make? Yes, sir?
I was off the internet, but it says Earth has a season because the axis is tilted. The Earth axis is always pointing in the same direction, so different parts of the Earth get sun different rays throughout the year.
Okay.
That's why we have seasons.
Okay, so let's explore that. Let's look into how does a tilt lead to our variations in temperature today. All right. So we're saying that there is most likely a tilt, and the evidence that we used for the fact that there's most likely a tilt was the idea that when we looked at our model, the sun doesn't get very high in the daytime sky in the winter months. We also noticed that the transit that the Earth moves during our daytime in the winter is a shorter transit than the sun moving through the daytime sky during the summer. And we said, well, the amount of hours in a day doesn't change, so that tells us the motion of the Earth must not change. It must remain constant. And if the motion of the Earth is remaining constant, the only thing that must be changing in this instance is the tilt at which the sun is directly, or the angle at which the sun's rays are directly hitting our Earth. Yes, sir?
Now, how would the bottom of the Earth and the top of the Earth get sun?
That's a good question. Let's try to observe that today in our lab.
The sun is that big.
Yeah, the sun is not nearly as close as that light source is to our globe. So right now we're just going to use our globe and this light source to represent what might happen with regard to temperature, either increasing or decreasing based on the tilted nature of our globe. So we've got a globe that's tilted, and right now if we're talking about the tilted nature of our globe, the northern hemisphere is tilted what? Towards or away from that light source? Away from. The northern hemisphere is away right now. And the southern hemisphere is then what? Comparative to the northern hemisphere. It is, and it's more direct to the sun, isn't it?
N through the Z, and sixth graders N through Z report to the gym for pictures.
Okay, so we're gonna take a temperature probe. And we're gonna put this temperature probe, I'm gonna turn the Earth so that Michigan is kind of facing towards the sun. So if I'm standing on Michigan and the sun is at its highest point during the day, what time of day are we most likely at? We're most likely at noon, somewhere around noon, right? Highest point of the day, the sun is most likely close to noon. And I'm going to use the very end of the temperature probe, which is what is reading temperature, and I'm going to put it right over Michigan. And this activity wants us to put that area, put the probe at the 45th parallel. Well, Michigan's pretty close to the 45th parallel. If we drive north on 127 up to 75, and you go right south of the town of Gaylord, there's a big sign right in the middle of the median that says, "Welcome to the 45th parallel. You are now halfway between the equator and the North Pole." So Michigan has the 45th parallel run right through it. Okay?
That's awesome.
So we're choosing a location, we're choosing Michigan, and we've got our globe set up to what we see here. Our sun is really kind of right directly in the middle of the globe right now. If I was to take this globe and say it's a perfect circle, I'm disregarding the equator. This is pretty straight on to the middle of the globe, right? And I'm going to take this and I'm going to kind of line it up just a little bit like so. And we are going to collect some data. And so if I scroll down here inside of our worksheet, it wants us to position the North Pole so it's tilted away from the lamp, as we see in the figure 1. We're going to position the bulb at the same height as the Tropic of Capricorn, which is 23.5 degrees. So the Tropic of Capricorn is the line that is at 23.5 degrees right down here. And so if we draw a straight line straight out, we're getting pretty close to that light bulb. All right. It then wants us to use 20 centimeter piece of string to place the light bulb 20 centimeters from the tip of the temperature probe. So I'm going to use just a measuring device for this. I'm going to move it closer so that it's 20 centimeters away. So we're going to say right about in there. The globe keeps trying to move on me. Maybe I should tape it so it stops wobbling. Online folks, can you kind of see this in the screen? You can see my setup?
A little.
Okay. Maybe I should move our camera just slightly. Maybe that'll help. And that might be as far as I can move the camera. Need a longer
This time we need the sophomores, A through G, and the seventh graders, A through G, to head to the gym, please. Thank you.
All right, we've got our temperature probe set up. Right now, our temperature probe, without turning the light on, is reading 23 degrees Celsius. So in our box, we're gonna probably record the initial temperature right here. So the temperature probe is set up, our initial temperature, 23 degrees Celsius. You're gonna record it right in that blank. And we are gonna turn on the lamp and we're gonna collect data for 5 minutes. And we're gonna record our lowest temperature, our minimum temperature, and our highest temperature, our maximum temperature.
Is it 23?
Yep, 23 degrees Celsius is what it's at right now. 23 on the dot. All right, so here we go. I'm gonna turn on the light, and I'm gonna start a timer. So after 20 seconds, our temperature is now reading 24.2 degrees Celsius. I'm sorry, what's that?
How many degrees is that?
How many degrees in Fahrenheit is that? Well, we can convert it in a little bit. Maybe one of you with a computer sitting in front of you right now could take 23 degrees Celsius and figure out how many degrees Fahrenheit it is. Ooh, 73.4. Oh, interesting. 73.4 seems to be very similar to what that thermometer on the other side of the room is reading. We have 1 minute, 15 seconds remaining of our data collection.
What's the temperature?
The temperature right now is 30.1 degrees Celsius. Nineteen seconds. Our temperature is 31.5.
It's like a 15 degree.
31.9. 31.9 was our final temperature. So our maximum temperature, 31.9, please put that inside of the data table. What was our minimum temperature?
23 degrees.
23 degrees Celsius. So take some time to figure out the difference between the two and write that in temperature change. I'm going to shut this off so that it cools off. Yes, sir.
There's only one worksheet and it's just assigned to you.
And we don't copy it. File, it was I make copy of it.
Did you go into the Google Classroom?
I just went to your,
Yeah, go into the Google Classroom, and there should be a copy for each of you. Right here, what causes the seasons. Right there, Alex Gifford. It's already got your name on it.
Temperature change. 7.6.
what was the first one?
All right. The first one was 23 degrees Celsius was our room temperature.
Maximum is 31.
I don't know what's wrong here in the second one.
What was our maximum temperature?
39, well, I mean 31.1.
31.9, right? 31.9. So what is our difference in temperature then?
8.6.
8.6 degrees Celsius. Okay, all right, we got our units. The next one, summer data collection. So how do we need to rearrange this globe so that we are collecting summer data?
Oh,
Raise the light, no, not don't raise the light.
well, once in the middle, it hits a certain temperature, then it doesn't go back up. A certain time of the year, it doesn't get cold anymore.
Okay, I agree. Certain time of the year it does not get colder. During the summer it doesn't get colder. What does the globe do, our Earth do around the sun?
It goes around.
Oh, it goes around. So if I'm at the winter, what time of year would, or how long of the year does it take for us to get from winter all the way to summer?
What, 6 months?
Oh, about 6 months, which is about how much of the year? Oh, about half of the year. So if we truly are orbiting around the sun, if I go half the distance around, and I'm still going through like day, night, day, night, day, night, over and over again, right? So about half of that distance is going to end up over here, right? Okay. And so now I can kind of spin around my lamp. And it's at the same height that it was, so that's good. Maybe I need to like I want it just like that right there. That's important. What was the other thing that was important that I kept constant in this experiment? The distance, right? The distance from the lamp to the light. So I want to keep that constant. So right there. Okay.
We gotta measure the distance.
All right. I kind of want my temperature to get back down to 23 degrees Celsius, but I'm not sure that it's going to get all the way down that far because I think the globe probably warmed up a little bit. Yeah, if I put my hand on it, it's still a little bit warm from heating it earlier. But I could try to cool it down just a little bit here. Try to get it close to 23 degrees again. We're at 28.2, so that might be kind of where we stay because I'm thinking the globe's probably going to stay a little bit warmer. So let's start our timer again. I'll start it as soon as I turn the light on. Our starting temperature is going to be 28 degrees Celsius. That's where we're going to start. So write that in the minimum temperature.
Is that 20 centimeters away?
It is at 20 centimeters away. Yep, I double checked that. We're 20 centimeters away. And we are going to turn the temperature on. We're going to run this for 5 minutes.
This is what you know, like, Alex.
Right, huh?
Mr.
What's the minimum again?
28.
Middle one.
Somebody online just asked a question. Or
Yeah, what's the minimum thing right now?
28.
28 degrees Celsius is our minimum temperature. So the globe kind of stayed warm from our last experiment. So it only got down to 28 instead of dropping all the way down to 23. But that's okay because we're looking at the difference in temperature. And if we really wanted to, we probably could wait for a while. Or I could have went and grabbed a different globe that maybe is already 23 degrees Celsius because apparently 23 degrees Celsius is our room temperature. Are you guys able to see the globe online, people? Or not so much? Maybe I need to move over here a little bit. There we go. Now you can see it a little better. So we've got our light source over here, and it's shining towards the globe. It's hitting our temperature probe. We went through half of the year, half of the movement of our planet.
What's the temperature?
Currently, right now, our temperature right now is
At this time, we need the
33.2.
sophomores, H through M, and the 7th graders, H through M, to head to the gym, please. Thank you.
Sophomores, H through M. Take off freshmen again?
Very good.
Did you get your picture already?
I'm sophomore.
You're a sophomore. Eli, did you get your picture already?
No, I didn't, girl.
You should probably go get your picture done.
It takes time.
It does take time, that is true. At our halfway point, almost our halfway point, we're at 35.9 degrees Celsius and climbing. So we're still measuring the temperature in Michigan. We're still at the 45th parallel. The distance away from our heating source is still constant of 20 degrees or 20 centimeters. Our globe is still slightly tilted, which is what we talked about the other day. That must be there must be a tilt to our planet. And the only change that we made in this portion of the experiment is we moved the globe halfway around the lighting source.
Yeah, but what about like the lakes? Because the lakes, it gets colder around them.
Oh, so you think maybe water on our planet might change some of this in specific locations?
Well, yeah.
Okay. All right.
How would we measure all of Michigan? Yeah, like go to every place.
Yeah, we don't have any way to be like, oh, we've got water around Michigan, and it's like put a bunch of water on our little imitation globe. Really, we're just looking to see what is the temperature going to do, either increase, decrease, or remain the same based on different points of the season, different points of the year. So we got 45 seconds remaining. Our final temperature is 43.7 degrees Celsius. 43.7 degrees. 43.7 degrees Celsius.
0.7?
Yep.
Oh, that's a big difference.
That is a big difference. Can you determine the difference?
Well, 0.7. Are you use my calculator?
Yeah, you can use a calculator, absolutely.
Oh, it's 15.7.
15.7 degrees temperature difference. So if we go down to processing the data, we would take those differences that we got for each of the charts and we'd add those differences into the blanks. So we said that the summer temperature difference was how much? 15.7?
Yeah.
15.7 degrees Celsius. So 15.7 is going to go here. Our maximum temperature is going to go here. And our minimum temperature is going to go here. So what was our temperature change for winter? Remind me. What was it?
31.9.
I don't think it was 31.9 being the difference. I think that was our final.
8.6.
8.6?
Yes.
Okay. What about our summer temperature difference?
15.
Oh, 15.7. Well, that's a big difference. So how does the temperature change for summer compared to the temperature change for winter?
18 point what?
15.7.
15.7. So how does the temperature change for summer compared to the temperature change for winter?
Well, in the summertime.
Oh, there's a greater temperature change during the summer than there is during the winter. Interesting. You should write that into this part.
Could you repeat that?
Yes, the question is, how does the temperature change for summer compared to the temperature change for winter? And what did we just discover? That we have a greater temperature change during the summer than we do during the winter. Thank you, Miss Hannah. So let's say that we go to spring, which spring is halfway between winter and summer. So instead of making half of our orbit, we would only make a quarter of it, right? So what do we think the temperature change would be for spring then? Okay, let's talk about temperature change. So we had the greatest temperature change during the summer, a lower temperature change during the winter. How is spring going to compare between these two? Jason?
Probably be around like 10.
Okay, why do you pick 10?
It's just in between 15 and 8.
Okay,
Maybe
excellent.
A little higher, but
Okay, it might be a little bit higher than 10 degrees Celsius change in temperature, he says, but he picked something right between 8 and 15. He thought that it'd be somewhere in between those two. Oh, and then it might be the same thing for fall. Oh, interesting. And so in fall, maybe our temperatures end up being pretty equal to springtime temperatures when we average them out, because we've gone all the way to the other quarter. We've gone 3/4 of the way around the planet.
I think fall would be like either 14 or 13.
Okay, so it's going to be cooler than the temperature change in winter, or in summer, excuse me. And it's going to be warmer than the temperature change that occurs during winter. Okay.
I disagree.
Okay, explain to me why you
I
disagree.
think in springtime it's only cold in the what's it called, in the morning time. And it's like dew on the ground, then it warms up.
Okay,
And yeah, for example, but fall during deer season, it's cold like all day.
okay. Today it's cold all day?
No, it's not ripe season yet, but during ripe season it gets cold.
Oh, so let me ask this. What would be the first day of fall?
Something in October, November.
It's in October or November, he thinks.
No, it was actually this month.
Oh, it was actually this month. Do you know an exact day that it was?
The 22nd.
Oh, the 22nd of September is the very first day of fall. And so do we notice in the morning, it's kind of chilly in the morning, but then it warms up throughout the day on the first day of fall? And is that what you were explaining about the first day of March?
Well,
Oh, so in the morning, it's kind of cool for the 21st of March, 22nd of March, the first day of spring. So it's kind of cool in the morning, but then as we move through the day, it tends to warm up quite a bit.
yeah.
Oh, no, it's the 21st.
Oh, it could be the 21st. I think every year it's plus or minus a day.
Yeah.
So we're thinking that fall and spring would have relatively the same average temperature change throughout the day. So I'm going to read this chunk of information that is inside of our lab. It says, we're going to read it and then we're going to answer the questions below. The sun's energy is transferred through outer space by the means of radiation. The light energy travels in a straight line all the way from the sun. The parts of Earth that are angled away from the light receive the energy, but indirectly, which means the light energy is spread out and not concentrated as much as when the light is more direct. Therefore, when light is more direct, it is more concentrated and will cause a greater temperature increase because more energy was transferred to that location. See the diagram below. So we've got indirect sunlight coming in from up here. And that indirect sunlight is hitting our planet. Down here, we have direct sunlight. So if I was to take a flashlight, and I was to shine a flashlight on our board, and I was to point that flashlight right directly at the board, would that be direct sunlight or indirect sunlight?
Correct.
It would be pretty direct. I'm hoping that online people, you can see this. So if I take my light and I shine it right at the board, it's direct sunlight. If I take this same flashlight at the same distance and I tilt it at 45 degrees, what happens to that sunlight or that light that's hitting the board?
It goes up just a little bit.
It goes up just a little bit, and that light is spread what? Oh. Alex, your master buddy. Thank you, sir. What is happening to that light? It's being spread where?
Internet failure for. Twice a day.
So I've got the light. This is direct. Maybe this helps. Maybe if I circle the light. I've got the light so far away, I'm circling it. Has the amount of light changed that's coming out of this light? No, it's pretty constant, isn't it? Now I tilt this at 45 degrees. And now I'm going to trace the light.
So you're trying to put more light with a bigger area.
Oh, not more light over a bigger area.
Same amount of light.
The same amount of light over a larger area. Isn't this what happens with our globe in this image that we're looking
Teacher,
at?
sorry for the interruption. Just want to make a quick announcement to all students. Please make sure upon entering and exiting the building that you are properly wearing your face coverings, and during lunch times when you are done eating, the expectation is that you are also wearing your face coverings appropriately. If you have any questions, please see me, but thank you for your cooperation and in following our procedures. Have a great day.
I do have one question for you.
So direct sunlight is going to hit near to the equator right here, right? Notice that we still have light that's coming in up here, but as that light makes contact with the spherical Earth, what's happening to that light?
With access to it.
Okay, there's some of that light is maybe missing up here, right? Some of that light is maybe spread out above the Earth. If I was to draw the light that is cast on this globe, what would it look like?
To a what?
If I was to draw the light that's cast on this globe right here at the top, what would it look like? Would it be a perfect spherical circle? What would it look like?
Province?
Maybe. Which of these two circles would it look like? The one at the bottom that was more spherical with direct light,
On the top.
or the one that's right here with more indirect
It's
light?
just space up there in the atmosphere.
Oh, it would be spread out over more area. So at the polar regions, because it's not direct sunlight, we have the same amount of energy come in, but it's spread over a much larger area. What does that do to temperature? Does what?
Decreases.
It decreases or increases?
Decreases.
Oh, it decreases. Because we have the same amount of energy coming in, but it's spread over a much larger area. We don't get as much energy that is stored there, right? So if we are getting less solar energy because it is spread out over a much larger area, our temperatures are going to be lower. So question 2, draw a diagram to compare and contrast how the light energy from the bulb heated the probe during winter and during summer. In order to draw a diagram, remember we're going to go to Insert, we're going to go down here to Drawing, and we're going to create a new drawing. And you're going to create a diagram for question number 2 of how that light energy from the bulb heated the probe during winter and during summer. Then I want you to go on to question number 3. During which season is the sunlight more direct? What is meant by direct in this context? You're going to explain. For number 4, you're going to use the diagram right here in order to show and explain where the sunlight is shining most directly during the first day of each of the 4 seasons. And then for number 5, what would happen to the temperature change if the Earth was tilted more than 23.5 degrees? You're going to draw a diagram to illustrate the reason for your answer. So again, remember to do a drawing, to do an illustration, I'm going to go Insert, Drawing, and I'm going to create a new one. If you get completely done with that and you wanted to, you could come up here and explore with the globe, and you could choose some different locations on the globe to measure temperatures, and you could do some comparison between them. I am looking for everything to be complete and turned in by Monday
There's more than just.
through question number 5. I'm not worried about 6 and 7 unless you get done with question number 5 and you wanted to do some extension work. What questions do you have? All right, you may begin.